Hello and welcome to Data Color Academy. My name is Milagros Watts and I am applications for the product management team at Data Color. Today we're going to go over sample measurement best practices. This is part 3 of the series Digital Color Management Fundamentals. Welcome. One of the key elements for a successful digital color management program is how accurate and repeatable can we measure our samples. If we don't develop a good technique to measure our samples, we will considerably reduce the accuracy of our color recipes and will have inconsistent results in the QC and inspection areas. There are many factors that affect sample measurement. We are going to go over the most important ones. As you can see, we have divided these factors into, first of all, the sample characteristics and then the instrument configuration. For the samples, we are going to go over how important it is conditioning your samples, how important it is to control temperature and humidity, how important it is to keep the sample's thickness to a point that the sample is opaque. And we'll discuss how many foldings, how many layers would be recommended for a good technique. We're also going to cover positioning of the samples and number of measurements. How many measurements should we take of each sample? And finally, we're going to go over the different types of samples and what are the recommended presentations for them. In the instrument configuration section, we are going to also cover how important it is to maintain consistent conditions and geometries across the partners involved in exchanging color communication. So we are going to cover aperture, specular, UV conditions, and the differences in the different geometries available today for spectrophotometer. We are going to briefly cover the new hyperspectral image spectrophotometer technology. So let's start. Most textile standards used to evaluate color visually and instrumental recommend that all areas used to evaluate color should be conditioned to laboratory standard conditions. This is temperature of 21 centigrades or 70 Fahrenheit and relative humidity of 65%. Maintaining large areas of color evaluation rooms or offices to evaluate color in controlled conditions of temperature and humidity is sometimes very expensive. So a conditioning cabinet is a better alternative. A conditioning cabinet allows to maintain controlled temperature and humidity conditions for our samples, and this is regardless of the location, whether if we are in an area that is more humid or colder or warmer. We frequently get customers asking us what variations in temperature and humidity really affect the color of our samples. In the table shown in this slide, you'll see a study that was done with 9 color samples ranging from browns, reds, oranges, greens, and blues. These samples were measured with a spectrophotometer in different conditions of temperature and humidity. The standards were set as the samples measured under laboratory standard conditions, and then variations between temperature and humidity was performed to account for what color variation can we see when we move these parameters in one direction or another. As you can see, the values in blue are showing delta is above 0.15 CMC units. And as you can also see, the most affected or the conditions that affected the color the most were conditions where the humidity was kept lower, in this case 35%. So the first column also shows larger variations for certain colors, and the increases in temperature or humidity do not seem to affect the colors that much. In addition to this conditioning of the samples, the thickness of the sample is very important. If the sample is not opaque enough when we place it in the instrument, we are not only going to capture the color of the sample, but we may capture also reflection from the sample holder. In the image, you can see a light pink chiffon sample that when we place it with one layer, we also are capturing the sample pad. So the only way to accommodate or to capture the color of the sample is folding the sample multiple times. The risk with that in this particular material that is very light is that we need many, many layers to be able to bring the material to be opaque. When we do this, the risk is that the sample is so bulky that it will protrude inside the sphere, like we can see in the image on the left. For these samples, sometimes it is a repeatable method to place one or two layers with a backing of a white tile, similar to the one we use to calibrate the instrument. So as you can see, placing a couple of layers, it offers a better sample presentation. This can be used only when the standard and the batch are evaluated in the same conditions and with the same white tile backing. If we want to capture absolute values of the color, this method will not work. Or if we want to match a color, this method will not work either. For typical knitted or woven materials, folding the sample one or two times will be enough to achieve opacity. In the example, you can see a blue cotton sample where we have made two foldings or 4 layers, and the positioning shows a very uniform, very clean presentation. And we have discussed how to present the sample, but what about accounting for variations in the sample itself? How we can account for variations in the fabric construction, in the directionality of the yarns, or if we have on-level dyings. The following video illustrates a good technique for samples that can be measured, fold first to achieve opacity, and then measure multiple times, in this case 4 times, with rotation and repositioning. So the sample is fold one time, then a second time, and we place it in the instrument and take the first measurement. When that first measurement is completed, we take the sample, rotate it, and repositioning in the other side. So we are rotating 90 degrees, but measuring in the back side. Then to complete the third and fourth measurement, we take the sample, refold it now in the other direction, and repeat the previous procedure. First at 0 degrees, and then rotating 90 degrees and measure it in the other side. This proves to be a very good method to measure our samples and capture the whole area of the sample. Now, this is only for samples that are uniform, that our variation across the sample is not that large. So 4 measurements seems to work very well for knitted woven materials as discussed earlier. But there are other materials. There are materials with more texture. There are materials that have high pile and so on. So the best way to develop an optimum measurement technique is when the sample can be measured, remove from the instrument and remeasure with a variation of less than 0.15 delta E CMC units. The number of measurements will depend, as I said earlier, it will depend depending on the material we are measuring. The following video shows a way to capture variations in measuring a sample multiple times. This shows data color tools. The first thing we need to do is make sure that we set our instrument to measure multiple times and capture averages. We're going to be measuring a blue standard. When we press OK, place the instrument, the sample in our instrument and measure. We can see the results of that measurement. Then we'll reposition the sample and measure it again. And as you can see, as soon as we measure the second time, the system shows now a deviation between the second and the first measurement. Developing a repeatable technique involves measuring multiple times to ensure that that deviation is kept below 0.15 CMC units, as mentioned earlier. We are going to measure the third time. And notice what happened when we measured the third time. Something was wrong with that third measurement because now the deviation of the three measurements is 1.52 units. So we will continue measuring a fourth time. And when we do that, we managed to lower the value, but still is 0.3. Removing the third measurement, and that's what is great about this option in the software, is that I am allowed to decide what measurements will be included in the average and what measurements will not. So including the third measurement for 5 measurements total brings the deviation to 0.2. When we remove that third measurement that we suspect that something was wrong with it, the value considerably is reduced. So that is a good way to know how many measurements you will need for your samples. Once you can start with 8 measurements, do the analysis, and if you maintain the value, and if you lower to 7 measurements and you maintain the value below 0.15, you can go down to 6, to 5, to 4, and so on. This will allow you to determine how many measurements you have to take of your sample. Following our webinar, we will discuss now how to present other types of samples that are not that simple as the knitted or woven materials. And we are going to talk about bulky and high pile fabrics. These include towels, carpets, fleece, fur, velvet, etc. The issue with these samples is when we place them in the aperture of the instrument, because of the nature of the material, the texture, the sample protrudes inside the sphere. So the way to manage this type of materials is to use a sample holder. There is one example of a holder we call donut. It's a cylinder with a rubber band. We would place the sample on top of the cylinder and use the rubber band to keep the sample uniform in a uniform way, flat, and to be able to manage the measurements. In the right, you can see without sample holder, and once we place a sample, we use the donut holder, you see the presentation of the sample now is much more uniform. So this type of material still will require multiple measurements with rotation because of the texture. For samples like loose fiber, we also challenge the same issue, protrusion in the sphere. We also are challenged with the fact that the pressure that is applied in the sample holder will vary depending on the user. So for these, we recommend to use a compression cell holder. Compression cell holder is made out of two parts. We will place an exact weight amount of the fiber on the on the right side of the sample holder, and then we'll close it with a lid and close it tight, like you see in this image in the center. So that way, the sample can be now presented to the spectrum without the bulging on the or the protrusion in the sphere. It is recommended that we use the same amount of fabric, same weight of the fabric, the fiber each time. And it's also recommended that we measure the samples specular excluded to remove the glossy effect of the glass. For yarns, we could use the previous compression holder, or we could use different presentations that are proven to be to produce repeatable results. One of them is winding the yarn in a card, like shown on the left. The other two presentations could be use a skein or yarn holder, depending on your sample. The yarn is placed in this the white part, and the springs allow to clamp the yarn in place. The only recommendation in this case when using these holders is to make sure that the tension that is applied be a controlled tension. If we do variations in the tension, we will have differences in color. So we cover in general general aspects of or recommendations for sample measurement. Let's talk about how important it is to maintain the same or consistent instrument configuration when we are exchanging a color across a supply chain. So it is important to control the aspects, and we are going to go over them. Regarding the aperture, what is the recommended aperture to use when we are measuring your textile samples? Again, the answer to this question is the first answer is how big is your sample? Sometimes we don't have any other alternative but using very, very small aperture sizes because the sample is very, very tiny, the sample that we have received from the customer. But in general, for submission of lab tips or for matching color or for routinary QC activities, the larger the aperture, the better we are. So we will see many brand programs where the recommendation is to use a medium aperture or a large aperture. In the following table, we are showing the effect of using MAV or medium aperture view versus a small aperture view or SAV. We're talking about a difference between 20 millimeters and 9 millimeters. We are measuring also samples that range from a very uniform woven sample to a more complicated texture like corduroy or a variegated rib or fleece, etc. So these samples were measured using these two apertures and were measured with average of 4 readings or 2 readings. The values that are shown in bold are all below, equal, or less than 0.15 delta ECMC. In other words, that is showing a good technique or a good result. The other values that are not bold are the ones that exceed the 0.15. As you can see, there are issues with corduroy when we use only 2 readings or we measure in SAV. And same with the variegated rib, we exceed values when we work with less number of readings or in a small area view. In general, the larger the area and the more readings we average, the smaller the delta E CMC values reported will be. So the aperture selection is very important to achieve less variation. What UV conditions should we use? Should we calibrate our instrument for UV? Should we include UV? Should we exclude UV? In general, many brand programs recommend to measure color samples with UV excluded. When we talk about optical brighteners, white materials, fluorescent white materials, or treated with fluorescent white agents, the recommendation is to calibrate the instrument for UV to be able to quantify the amount of UV that we are using to measure our samples. The only way to calibrate the UV content of the lamp, and the reason is because as the instrument age, the UV content of the lamp changes, is to use some whiteness standards. And these whiteness standards are typically ADCC or Hohensteiner, or sometimes the provider of the spectrophotometer offers a calibrated fluorescent dial. The two methods we typically, or the two whiteness indices we typically recommend are the Ganz Greaser whiteness and the CIE whiteness indices. CIE works with a specular included. Ganz Greaser works with a specular excluded. Again, whites are not evaluated in terms of typically not evaluated with differences in color differences, delta E. They are evaluated more with whiteness and changes in tint. Let's talk about geometries. It is clear probably for most of you that there is no compatibility between an spherical geometry and a directional geometry. So when we hear that brands recommend diffuse 8 degrees, if some of the suppliers are measuring with 45-0, there will not be a good agreement between those two measurements. So another important aspect on exchanging color digitally is to use the same geometry. This is a very simplified diagram of a spherical diffuse 8 degrees geometry. The reason why it's called diffuse 8 is because the lamp hits the walls of a sphere and the light goes everywhere in multiple angles, and that diffuse lightning is hitting the sample. Then the 8 degree is because the lenses, the detection happens at 8 degrees of the normal of the sample. This geometry, diffuse 8 degrees, also offers a specular port or a gloss trap that can be included or excluded depending on the type of samples. When the port is closed, we are including the gloss or the specular component in the measurement. When the port is open, we are excluding the specular component on gloss from the measurement. When we talked earlier about using the compression cell holder, we discussed to measure these samples with a specular excluded. In other words, we are removing the glossy effect from the glass. This geometry is typically used in the textile world for QC and formulation. We have another geometry called D0 or diffuse 0 degrees. Same principles. There is diffuse lightning in different angles hitting the sample, but in this case the lenses or the detection happens at 0 degree of the sample. This geometry does not have a specular port, so all the measurements are specular excluded by default. This geometry is typically recommended for paper and paper manufacturing products. Some uh, uh, color standards for the textile industry uh, could recommend diffuse 0 degrees as well. And then we have the directional geometries. We'll talk about 45-0 and 0-45. In the particular case of this geometry we are using here is a circumferential 45-0. There are multiple lamps or fiber optics always hitting the sample at 45 degrees. So that's why we call it 45-0, because the lamp is placed at 45 degrees and the detection, the lens is 0 degree from the sample. 45-0 or 0-45 is typically recommended for automotive or footwears or other materials, sport materials or backpacks and other type of materials used where the samples, there are multiple components and the components are made out of different materials. So textile and plastics and vinyl, they all have to be the same color, but we know the appearance of these materials is different. So 45 0 degree geometry helps to account for that appearance aspect. 0-45 is basically a case where now the lamp is or the illumination happened at 0 degrees and the lens are capturing the information coming from the sample at 45 degrees. So same applications for, as mentioned before, for automotive, footwear, etc. We've seen so far measurement of materials that are solid, um, single color materials with different textures. But what about these samples? What about multicolor prints? What about lace or all the trims that are used for garments, zippers, buttons, etc.? There is a new technology called SpectraVision. It's a hyperspectral imaging spectrophotometer. It basically is a combination of a spectrophotometer with camera that allows to capture these materials, allows to capture multicolor prints. In the example, we have a sample with 4 colors. And what happens is the instrument will take not one measurement, but it will take 31 measurements. Basically, it's 31 pictures of the material. And that's what we're illustrating in the image on the right. There would be 31 images taken at different wavelengths from 400 to 700 nanometers. Every time we take an image, we are capturing the pixels of the whole sample and separating the color. This separation of color will enable the system to determine a reflectance curve for each of the colors in the print. In reality, this camera has very high resolution. It's 821 by 821, and we are talking about that each pixel is potentially has a potentially a reflectance curve. So the system measures the sample, group together and average together all the pixels with the same color based on a tolerance and generates one reflectance curve for each color. In the video, I'm going to show you very quickly how we can measure a red lace sample using this technology. It's a rendering of the possibilities that we have, very quick. And on a material that typically is not possible to measure with a regular spectrophotometer without capturing some of the background as we seen before. So it uses a very similar program called Tools SV. We are measuring a red lace sample against a solid red standard. So the system shows in the screen the measurement of the lace sample, the user will make a selection with this number one here of the area of color that we want to do the separation on. Once the color is separated, as you can see, the image is showing the color that is being captured or separated. We can adjust the border to include more or less of the material. We can change the name. And as you can see, we are discarding the background. The system is automatically discarding the background or the sample pad. So only the actual lace is going to be separating it to generate a reflectance curve. When we press done, the information goes to the analysis screen where you can see we now have reflectance or color difference between the standard and the red lace sample. This completes the presentation for sample measurement best practice. Next, in the digital color management fundamentals, we're going to cover the topic, put your colorimetric pass-fail decisions to the test. If you want to learn more, please visit us at Datacolor and sign up at Datacolor Academy for more classes and lectures like this type. Or if you want more useful reading material, please follow our Datacolor blog. Thank you and have a good day.